into distance. That concept is right, but when we consider in this case, a slight difference is there that we will learn today. And what about the somebody give me the query that the third problem is somewhat difficult. Is it the second problem we can do by means of the sine rule? Third problem is same as that of a taper, cylindrical taper, isn't it? And we already done one problem regarding this problem. Sorry. Yes. Good morning, Ranjit. Regarding the rectangular taper also. That means like that way you have to find out, you have to consider a small strip. Here, in the case of a strip, two things are get varied. In the case of a cylindrical taper, only diameter get varies. But here, in the case of a rectangular strip, two items get varied. Which are they? One is width and other is thickness. That you can see here. Width of the strip and thickness of the strip. Okay. See, width of the strip and the thickness of the strip is get varied. Can you recollect that? How we perform that in the case of a cylindrical taper? Okay. Diameter is varying from D1 to D2. And we consider a small strip at a distance x. Can you recollect this? Then what will be the slope here? Say this much is of length L. Then the slope will be what? D1 minus D2 divided by L. Then for this small distance x, what will be that? D1 minus D2 divided by L into x. Am I right? This much will be the slope there. Then what will be the diameter of this area? Sorry, this section. How can I find out? Say D1 minus this much, isn't it? Like that way, you have to check the width variation as well as the thickness variation. Both things you have to check. Say W, delta W or Wx equals what? W1 minus W2 divided by L into X. And say T is T1 minus T2 divided by L into X. Suppose this X distance is taken from here. X distance is taken from here. Okay. Can you change this equation? Here, instead of taking the x from here, I took that x from the smallest side. Then what will be what change you can see in the equation? In this case, the diameter here is small, here is large. So you have to add, isn't it? D2 plus D1 minus D2 divided by L into x. Am I right? If I take the x distance from the smaller diameter portion means, yes, Mugudan says it is, we have to write plus. What about others' opinion? Can you follow me? Can you follow me? Yes, okay. What about others? Jagannathan? Mukesh? Okay, fine. So like that way you have to do this, solve this problem. Instead of only one variable, here two variables are there. That is the only problem. And finally you have to integrate. So I shall send you that solution. Where is that? Here we will get the equation like this. Stress in the strip is equal to this much. And then strain in the strip can be find out. And finally you will get the delta L. To get the total deflection, you have to integrate from 0 to 200. Okay, so that is in the next page. I am integrating from 0 to 200. And I did this calculation with the help of calculator. Do you know how to do this calculation by using calculator? Okay, Jagannath, fine, fine. Do you know how to calculate this with the help of a calculator? So I got here like this. No, okay. Dx divided by 20 minus x divided by 40 into 2 minus x divided by 200. So you can proceed like ln 20 minus 40 plus ln 2 minus x by 200. Like that you can write and then you can proceed, isn't it? By means of that we can proceed ln by means of normal integration. And here I am going to perform it by means of a calculator. That is, let me take calculator. All of you please take the scientific calculator. Ready? Are you ready? Okay. What is your model number? Okay, 991 ms. Okay, me also 991 ms itself. Okay, fine, no problem. You can see on the top layer of buttons, you can see a mode button. Casio FX 100, FX 82. Yes. Okay, FX 82. Is there any symbol like this integral dx? Not for others. Polraj, please wait. Jagannathan and Mukundan. Okay, fine. That is there. No, that means your version is very low. So in that calculator, you can't perform the integration. Okay. So you can't do that with the help of calculator more than. Let us see how we can perform it with the help of this 991. Let me explain to others. So that is, okay, fine. So integral dx. So before that, you can see on the top layer buttons, all others, please listen. Shift alpha, then mode and on switch, isn't it? You can see a mode button. Click on that mode button. You can see COMP is 1, CMPLX is 2, like that you got, isn't it? Click on 1. After getting that window, click on 1. Now you select the computer mode, COMP mode. Now you select the COMP mode. Okay? Okay. Now, please listen to the whiteboard. I can write like this equation like this. 20 minus x by 40, the whole raised to minus 1 into 2 minus x by 200, the whole raised to minus 1. Am I right? Integral symbol is there. Okay. So here, how to type it on the calculator is, first of all, press integral dx button, and then integral dx will be like this, but don't do it now. Integral dx will come like this. Okay. This is an inbuilt symbol and an inbuilt bracket. Okay. No need of closing this bracket. Now, after that, you have to open a bracket according to your use. So I open one bracket and type 20 minus x by 40. For that, I have to open once again a bracket, x divided by 40. And then I close the bracket and close this 20 bracket. So up to this bracket is closed. Then you have to press a symbol x raised to minus 1. Say press x raised to minus 1. So that part over. Then press multiplication symbol and then open a new bracket and write 2 minus x. For that a bracket is open, x divided by 200. Bracket closed, and again the main bracket is also closed. Press x raised to minus 1. That's all. And then you have to give the limits. Okay. For that, comma 0, comma 200. That's all. This is the way how you have to type. No need of giving the final bracket. This is the how you have to do it on the calculator. And before that, how I got this x here. For that, you can see on the top layer alpha. Can you see that a red colored lettering is there, alpha. After clicking alpha button, you can see that near to the bracket symbol, in the top of a bracket symbol, you can see the red colored X. Can you see that? Okay. Alpha, this bracket symbol will give the X. Am I right? Have you got? Alpha, this bracket symbol will give the value of X. Yes, fine. Now we can perform. Let us see. All of you press the integral dx symbol. Have you got like this? Okay. Have you got the symbol like this? Now you have to write, put another bracket. All of you please put another bracket and then type 20 minus. Again a bracket you have to open, x divided by 40. Bracket closed and the main bracket is also closed. X divided by 40, bracket closed. Up to that clear? Then you can see near to integral dx, that is, it is like this. Integral dx is like this. And then you can see a bigger button. After that, you can see x raised to minus 1. Am I right? X raised to minus 1 you can see on the top layer. After typing this much, press x raised to minus 1. Simply press x raised to minus 1. You can see on the display minus 1. Have you seen? Okay. What about others? I can't get any. Yes. Okay, fine. After that, you have to put the multiplication symbol into. Then again, you have to open the bracket. Then type 2 minus. Again, you have to bracket. Then open the bracket. X divided by 200. Bracket close. Main bracket closed. Into. Sorry. X raised to minus 1 you have to type. That means simply press x raised to minus 1. So you will get minus 1. Do it. 2 minus x divided by 200 minus 1, 200. Have you reached up to this? Have you reached up to this? Then after that you have to put one comma. After that you have to put one comma. How can you put the comma? That is a bracket symbol you see. After that you can see a comma button. Have you seen? Yes. Press on that comma button. You can see the display the comma. After that is 0, then comma, then 200. Then press equal to button and wait for 5 seconds. It will take some time for calculation. Yes. After 200, nothing. No need of closing the bracket. Yes, 8.1093 is the right answer. And then you have to do the remaining task. That means, see, this is not the final answer. You have to do with some multiplication also. Say 15 into 10 raised to something divided by 210 into 10 raised to something. That also you have to provide. Still screen is blank. Yeah, wait. It is doing the calculation. It takes some time. This is the value of x. Yes, too much time. Still not you got? No, no, Mukesh, it is not the value of x. It is the value after performing the integration. We are putting the value of x as a 0 and 200 and we are performing the integration. Am I right, Mukesh? Yes, Paul Raj is right. At the time of the integration, we put the value of x as a 0 and 200. After that, we will get the value like this on subtraction. So that we very easily we got from this one. So is it clear? Is it easy to perform it by means of calculator? Okay. Ranjit, you got comp mode, computer mode. Still blank. Maybe some problem for your calculator. Math error. Some bracket or sometimes you put doesn't put any comma, like those things will be there. Okay, Ranjit. When you scroll, when you can scroll on where we make the problem, where you make the problem. When you check any other bracket or any other comma, you forget to put. Can you repeat? Sure. First of all, integral dx. Press the button integral dx. Then you will get the symbol like this. Then you have to open a bracket. Okay. Next is type 20 minus. Again, you have to open a bracket. X divided by 40. Then close this bracket and close the main bracket. So this bracket closed. Then press x raised to minus 1. Then press x raised to minus 1. You will get minus 1 like this. Then press multiplication symbol. Then again you have to open the bracket. 2 minus, again you have to open a small bracket, x divided by 200. Bracket closed. The main bracket is also closed. Then press comma 0 comma 200. Renji, did. Okay. Press equal to button. Yes. Okay. Fine. So like that way you can perform it by means of calculator. Okay. Fine. Now we are moving to today's class topic. That is, today we are going to learn the strain energy or work done. And in this, we have to learn with the introduction, then resilience, then proof resilience, modulus of resilience, types of loading, the strain energy due to gradual load, sudden load, impact load, and shear load. And after that, somewhat problems. Okay, moving to whiteboard. So when I give a tensile force to this material, what will happen? It will elongate. Am I right? It will elongate. And then what will be, sorry, it will elongate. And when I release this force, if this elongation is within the elastic limit, means what will happen? It will regain its original shape. Am I right? Yes, back to original conditions. Can all of you agree with that? If it is within the elastic limit, if I release the force, means it will come back to its original condition. Got it? Then my question is, why it comes back? Why it comes back? Why? Because whenever a force is given to that material, somewhat energy will be stored inside that material. Say we can say that a revenge energy is stored inside that material. Okay. And it is because of that energy, because of that revenge energy or utilizing this revenge energy, it will regain its original shape. And that energy, which is helpful for the material to regain its original shape, is called as strain energy. Is called as strain energy. You got the concept? What is strain energy? Okay. So what is work done? That we all know. Force into distance. Am I right? Force into distance is the work done. Isn't it? Yes. Here, the strain energy is raised or raised due to this work. Am I right? Due to this work, the strain energy is raised. How here the works come? F is the force or P is the load applied and resulting in a distance of about delta x. So P delta x is the what? Work done. And that work done result in the formation of storage of energy. Am I right? That work done result in the formation of strain energy. Or very simply, I can say that the strain energy is equal to work done. Is equal to work done. Can I? Why? Because using that work done or using that energy stored by means of work done, it will regain its original shape and size. That means no energy is wasted. Yes, energy is conserved. Okay. So that is strain energy is equal to work done. We can say like that. Okay. So based on this concept, we will derive expressions for different loadings. Say gradually applied load is there, suddenly applied load is there, impact load is there. So those for those things, the strain energy will get varied. That can be find out based on this concept. Strain energy is equal to the applied work done. Okay, is it clear to all? So you got the concept? Okay, what about others? Give me the response. Okay, fine. Next is we are moving to another one, that is resilience. Resilience. How much energy, or sorry, total strain energy that can be, that is stored inside a material is called as a resilience. The total strain energy that is stored inside a material is called as the is called as the resilience. Okay. Then what is mean by proof resilience? Proof resilience, that is the limit for that material to store that energy. Can you say how we can govern this limit? Based on elastic limit, isn't it? Based on elastic limit. If I extend a material beyond elastic limit means it will not come back. Why? Because it will enter into the plastic region. Am I right? It entered into the plastic region. So it will not come back to its original shape when it reaches the plastic region. So the proof resilience is means what? Maximum strain energy that can be stored in the material. Maximum strain energy that is just below the elastic limit. That much stress can be given to that material to get a corresponding strain. Okay. And that stress which is given to that material to get this proof resilience is called as proof stress. Can you follow me? Okay. Now, next is modulus of resilience. Modulus of resilience. Okay. Resilience again. Okay. That means 1 minute. Let me take a whiteboard. Say material is here like this. I give one force like this and another force like this. Say this horizontal direction and vertical direction, the load is acting. Okay. And um, after some, sorry, due to this force, it get elongated by means of this one and it get elongated by means of this one. This much. Okay. That much is happened. sorry, not like this. Because of this force, it get elongated to this one. Because of this compressive force also, it aids to the elongation itself. So this much of distance is traveled, x1 plus x2. Okay. So what will be the work done? F into x1 plus F into x2. Okay. This will be the work done. So what will be the strain energy stored in the material? That will be same. U is equal to Fx1 plus Fx2. Okay. So the total strain energy stored inside a material when an external force is acting upon or external work is done, then, sorry, external work is done, that is called as a resonance. How much energy that can be stored inside that material? Sorry, not how much. What is the total amount of energy stored inside that material due to the external forces? That is called as resilience. Next is proof resilience is there. That means how much external force can be given to that material in such a way that it can store or it can generate strain energy, or the limit up to which the strain energy can be limit for the storage of strain energy. Limit for the storage of strain energy. What will be that limit? That limit will be the elastic limit. We know that the material can regain its original shape only if you give a force which is less than elastic limit. Am I right? A body can regain its original shape only if the force is less than elastic limit. Yes, fine. If I give a force more than that means it will not come back. So that limit or that limit of storage of storage of strain energy in the material is called as proof resilience. Is called as proof resilience. Maximum strain energy that can be stored inside a material. And that stress for making that maximum strain energy is called as proof stress. Got it? Is it clear to all? Okay, fine. Now, modulus of resilience. Modulus of resilience means it is a ratio of proof resilience divided by unit volume. Proof resilience by unit volume is the modulus of resilience. What is meant by proof resilience? What is meant by proof resilience? Energy up to the limit. The maximum strain energy that can be stored inside the material is called as the proof resilience. Proof resilience per unit volume is called as the modulus of resilience. Okay. Now we are going to discuss the types of loading. First type of load is gradually applied load. Gradually applied load. Say, I took an example. A crane is here. And this is a crane. And this is a chain. And a load is there. And this is the platform. This is the platform. On this platform, you have to place this weight. Okay. And this is very slowly placed. Say it is coming down, it very slowly, and it touches one portion, and very gradually it is placed on the surface of this platform. Very gradually. Okay. Such a type of loading is called as gradual load. Is it clear to all? That means very slowly we are placing one material on a platform or on a surface, or very slowly we are applying a force on a material starting from 0 to maximum. Am I right? Starting from 0 load to maximum weight. Isn't it? Starting from 0 to maximum. Agreed? Yes. So what will be the average force? What will be the average load acting on this one? It is starting from 0 to maximum, isn't it? The 0 to maximum is the load acting on this one. So what will be the average load acting on this one? It will be P by 2. Am I right? Because in the initial stage, the load is not completely acted upon. Only a to 10 percentage of load is acted upon. Then it rises to 20 percentage, then rises to 30 percentage. And at last, only it comes to 100 percentage. So it has to suffer an average load of about half of that load during its application. Am I right? Okay, fine. Now we are moving to explain this gradually applied load. So you please consider a metallic bar having where P is the gradually applied load, P is load gradually applied, then A is the area of the bar, and then L is the length of the bar, E is the elasticity. But after placing it is a full load at rest. It is resting there. No more deflection will cause. Only the deflection, that means, see, if I put a load or if I give a load on that material means it will get deflect. Agreed? It will get deflect. Okay. So here, instead of giving that full load, I place it one of the corner so that deflection will be here like this. And then this middle portion is also placed so that deflection will be like this. Then full portion is placed so that deflection will be like this. Am I right? So the total strain energy stored because of this deflection will be what? Average of this one. Because it is very slowly it is applied over there. So the average energy stored will be the half of the load applied. Why? Because it is starting from 0 into this much total deflection, delta L. That will be the total work done. Got it, Mugundan? Okay. E is the elasticity. Delta L is the deformation. U is the strain energy. So we are going to find out the U there. 1 minute. Here my power supply has gone. And now my laptop is of 7%. So please wait. Let me take another source. Okay. Okay, please wait.